Great to see you here again. In this next video, I will talk about the greatest common dividers as linear combinations. We'll look into some lemmas and some theorems that we can find around this, and there are some important definitions or some important terms that we are going to define here and that we will need later in this chapter and the remainder of the course. First of all, we have to say the greatest common divisor and Bézout's theorem. There is a mathematician Bézout who created a theorem, and one of the elements that are, let's say, at the start of this theorem is that we can state that the GCD, the greatest common divisor of two integers a and b, it can be expressed as the linear combination of these integers, and it is expressed in the form SA plus TB, with S and T being integers. So basically that's what we know when we have a greatest common divisor or divisor that we can use, and now we can call it, or the expression of this is in fact part of the Bézout's theorem. The Bézout's theorem says if a and b are positive integers, then there exist two integers s and t, for which we can write that the greatest common divisor of a and b is a linear combination of a and b, with the coefficient of a being s and for b being t, both being integers. Now, when we look at this, we can define let's say what we call the Bézout's identity. Now, when we have a and b positive integers and the integers s and t, so that we can write the greatest common divisor of a and b equal to s times a plus t times b, then s and t are what we call the Bézout coefficients of a and b, and the identity GCD of a and b is equal to s times a plus t times b is called the Bézout's identity. And we will find ways to identify those two parameters, s and t. Now, when we want to find those coefficients, we can find them quite easily when we have a simple expression, the greatest common divisor between 6 and 10. We know it is 2. Because we have 2 times 3 and 5 times 2, but we can easily find here that 2 can be expressed at minus 3 times 6 plus 2 times t. So we have minus 18 plus 20 is basically 2. So the Bézout coefficients here are minus 3 and 2. Now, for more complex equations or identities, this can be a little bit more complicated. So we have to find a way, how do we find those Bézout coefficients? Now, what we are going to do is use the Euclidean algorithm to determine the GCD of two positive integers. And based on that, we're going to find what we call the Bézout coefficients. The first thing what we do is to find all those expressions. We find the GCD using the Euclidean algorithm. That's what we call the forward pass. And then we're going to transform from the result. We're going to transform the intermediate result in it to find finally those Bézout coefficients. Now, let's have an example here, and we look at a forward pass. We have, in fact, the greatest common divisor of 215 and 65. Now, we can say here that 265 is Q, the quotient 3 times 65, plus the remainder is 20. And based on this, I can say that the remainder is equal to 215 minus 3 times 65. We can continue, and now we can say that 65, the greatest common denominator of 65 and 20, we can say that 65 is 3 times 20 plus 5. So we have 60 plus 5 is 65, and we can bring 5 to the left-hand side, which leaves us that 5 is equal to 65 minus 3 times 20. The last element here, we find that 20 is 4 times 20, it should be 4 times 5, and that's the end of the forward pass. Now, the backward pass, we use the expression 5 is equal to 65 minus 3 times 20. And now we transform in here the previous expression. So we can put 65 in here, and we see that 5 is 65 minus 3 times 20. And those 3 times 20 can be replaced by 215 minus 3 times 65, because we have that on the first line. The 20 is 215 minus 3 times 65. So when we calculate this, we find that 5 is 65 minus 3 times 215 plus 9 times 65. We can finally write this, that 5, the greatest common denominator, is in fact 10 times 65 minus 3 times 215, which makes that 10 and minus 3 are the Bézout's coefficients. So that's basically what we wanted to know here. We wanted to have the GCD, the greatest common divisor, as a linear combination of the two numbers that we calculated the GCD from. Now we can do some more things. We have to complete some other properties like this new lemma. So when we have three integers a, b, and c, such that the greatest common denominator is a and b, of a and b is 1, and a divides b and c, that also means that a divides c. We can prove this using both the Bézout theorem and the theorem of divisibility. We know that the greatest common divisor of a and b is 1. So we can say that the linear combination of a and b, s times a plus t times b, is equal to 1. And when we multiply both sides with the integer c, we can say that s times a times c plus t times b times c is equal to c. From the video 4.11, when we have the division algorithm, we have proven that if A divides C, then A divides TBC, and because A divides SAC, and A divides TBC. Now, basically, that's the first element, and the second element that we can conclude, in this case, that A also divides SAC plus TBC. So following this, we can also say that S times A times C plus T times B times C is equal to C. That's the same result we had before. And basically, based on this, we can conclude that A divides C, because we can in fact divide by C, both ends by C. So that's the lemma, that we have those three integers and we can use this relationship of divisibility. Now, we also have uniqueness of prime factorization, and this lemma says that if P is a prime and P divides A1, A2 up to AN, where each AI is an integer, then P divides AI for some I. It means that we have a prime number and P divides that number that we have, then there is at least one number for which P divides that number. Now, when we look at this lemma, we can use a proof of contradiction. And let us assume that an integer n can be written in two ways as a factorization of prime. So we have two ways to write n. We have a different factorization, so the p1 up to pn are primes, and q1 up to qm are also primes. Now, the fact that both of them are equal, we can in fact remove the primes which are, let's say, identical, which are part of both numbers. So when we look at the primes, we order them in non-increasing order. So they P1 is the lowest one, then P2 up to Pn, and the same for Qn. So we have them ordered, and we can eliminate the primes which are identical easily. Now, when we would remove all those primes, we would have a product of primes equal to another product of primes. But this is impossible that both products are the same, or if they would be different and they would be not equal to each other. So basically this means, since this is impossible, it means that there is only one unique way to factorize integers. So we cannot find two different ways to factorize integers. Let's have a look at the multiplication and division of congruences. When we look at the congruences, and then we can easily prove that both sides of a congruence can be multiplied by the same integer and the congruence is kept. For example, we have 16 is congruent with 10 modulus 6. It means that 6 divides 16 minus 10, which means 6 divides 6, which is of course correct. When we multiply both sides by 3, we find that the multiplication here gives that I have 48 is congruent with 30 modulus 6. Now when we take 48 minus 30, which is 18, and we can conclude that 6 divides 18, because 6 times 3 is 18. Now, on the other hand, when we consider a congruence, the same congruence, 16 is congruent with 10 modulus 6, and we divide both sides by 2, we obtain 8 and 5, and now we have to see if 8 is congruent with 5 modulus 6. The question we have to ask is, does 6 divide 8 minus 5? So 6 divides 3? No, that's not possible. So basically the congruence is not kept, and we cannot say that A is congruent to 5 modulus 6. Basically we have to say that 8 is not congruent with 5 modulus 6. And the definition of the congruence, the initial definition by 2, left-hand side and right-hand side divided by 2, is basically not keeping the congruence. Now, when we look at the congruence, we can divide a congruence by an integer if this integer is relatively prime to the modulus. So we have to find an integer which is relatively prime to the modulus. And now we have to find the way to do this. We can write this as a lemma, and we can say that we have m a positive integer and a, b, and c being integers. When we know that a times c is congruent with b times c modulus m, and the greatest common divisor of c and m is equal to 1, then we can say, when we divide both sides by c, we get that a is congruent with b modulus m. Let's do that with an example. We have a equal to 6, b equal to 10, and c is equal to 3. Then we find that m is equal to 4. So we can say 10 times 3 is congruent with 6 times 3. So basically what we have here is that we have 30 and 18 on the other side. What I can say, does 4 divide 30 minus 18, which is 12, so 4 divides 12, yes. The next thing we have to do now, we divide both members by 3, and we know that the greatest common divisor of 3 and 4 is 1. So there is no common prime, that a common number that divides both. So the greatest common divisor is 1, and we can divide both sides by 3. So we find 10 is congruent 6 modulus 4. It means, is this correct? Well, 4 divides 10 minus 6, and that's correct because we have here 10 minus 6 is 4, so of course 4 divides 4. So these are the elements about the congruences, about the properties that we will use later. This was what I wanted to tell you about the Bézout coefficients, the linear combination of the greatest common divisor, and also the application on the congruences, how to multiply congruences and how to divide congruences. We will apply these later in this course, of course. Now, one of the things that we're going to do, we'll be looking at a next paragraph, which will be about solving congruences. You're doing a great job, so this video is finished, but there are still a lot of videos to come. I'm looking forward to seeing you in the next video, and I thank you. Bye-bye.